It's not for you.
Right, it is 2:11. Let's get started. Couple just reminder things. There's no classes next week, just in case you make sure everybody knows, right? Like just finals, no classes, just finals, no classes. What else? I have posted a few things in Canvas for you all that I mentioned, but I just want to make sure everyone sees them. So there's the evaluation of me. Everyone should do that, please, when you have a chance, like 5-10 minutes. It's anonymous, so whatever you say, I won't know who said it. I'll just know that someone said it. So you can say good things, bad things, criticism, whatever. I will read it all eventually after my supervisor looks at it and compiles it. But the more important thing here, well, I mean, that's important. Please do it. Like the more people that do it, the better. It's good to have a high response rate. As far as the final exam prep material, we have the final review, which I handed out last Tuesday. I had copies of it, but I think they all got taken. If you want a physical copy of it, I'd be happy to print one out for you after class. There's also solutions to that, which I will not print out because they're long, but they're posted on Canvas right here. Then there's the final review that is up there, which is from Chalmers from a previous quarter. It looks like this. It looks like, I guess I could actually click on it. That might just be easier. I could click on it. You can see it. It looks like that from 2023, a fall. So I think that's worth looking at. We might look at some of it today. And then going back to the modules here for just one more moment. There's also a list from Professor Lewis's class of just all the topics you should know about for his class. It's probably pretty applicable to both the other classes as well. There might be a couple things on there that are a little bit different, or maybe your teacher said, we're not going to have this on the final, but he is going to. So pretty general, good to look at. And then there's the practice final from Alvarado's class. I imagine he will eventually post solutions. If and when he does, I will post them. If he doesn't post them soon enough, someone has a final on Monday, right? I'm not really like, it is one of the finals on, maybe I'm thinking my 17B class. Okay, let me ask a different question. When is Varn's final? Wednesday. When is Lewis's final? Right. When is the other teacher's final? Who's the other teacher? When's Almeda's final? Right. Okay. So, right. So nobody has a final on Monday. Great. So if he hasn't posted the solutions before Wednesday, I'll write up some solutions just so that the people who are taking their finals on Wednesday can have that as a resource as well. Thank you. Did everybody get the sign sheet? And then there was one other thing I wanted to say before we got started. Where did you go, brain of mine? Sorry, I don't remember what I wanted to say, but so this is the stuff from Lewis. It's a fairly lengthy list here of the things. And then lots of suggested practice problems as well. So if you're looking for more practice, this is a good thing to look at. There was literally another thing I wanted to say though. Oh, I know what it was. I figured it out. Office hours next week. So next week, my office hours will not be as usual. They are different during finals week for everybody. But if you look in the announcements, I posted them. And it's pretty much every day from 11 to noon and 1 to 4, except for Thursday, not 11 to noon. So there's my office hours. They're all going to be in the library in the lower level down where drop-in is. So that's where you can find everybody during finals week. None of us, neither myself, nor Grant, nor Jen, nor Sarah will be anywhere other than there pretty much. As well as student tutors. So even when I'm not there, you can find help from other people as well. Questions about any of that? There's one other thing that just crossed my mind. So let me close this here. Close that. Sure. Yeah, you're not important. You're not important. Do you feel like sorry, there's things that keep just running across my mind. I'm like, what else is there? There's something else. We don't typically hold office hours on Friday though. So what time are the exams on Friday? 3:30? 8 a.m. 3:30. Might have to, let's see. Yeah, well, if there's an update on the office hours, I'll let you know. But generally, we don't have office hours on the last day of exams. So we'll see about you 3:30 people if we need to do something. I think that's all I wanted to say. Oh, I know what it was. Yeah, the other thing, I think I already said this, but I'll say it again. I am planning, I'm planning on taking this Chalmers review that you all have in your hands, or most of you have in your hands, and writing solutions to it, but also making a video of me writing solutions to it so that you can, if you prefer to watch a video, which I do not, I would much rather read solutions than not watch a video, but people have different tastes. So I'll make a video of me doing that. It might take a little bit of time to get posted. I'll try to get that up tomorrow. So yeah. All right. I think that's all the business things I had to say. Any questions, comments, concerns? All right. Oh, gee, wow, that's smooth. Okay. Sorry. All right. This cord over here is very sensitive. So you have a final next week. Today is what, the 12th? Oh, happy repeal day. You guys are like, what are you talking about? It's the day that prohibition was repealed many, many years ago. So that's why people who are over 21 are allowed to drink alcohol in the United States, because we repealed prohibition many years ago. So happy repeal day, December 5th. I will certainly be celebrating later. Anyway, you all should not be, because you should be studying for your finals. Also, most of you might be underage, although maybe not all of you, I don't know. But anyway, you should wait till after finals to celebrate in whatever way you wish. So what's going to be on your final? Good question, right? That's because really that's what you should be thinking about. Like, what kinds of things can you expect to see on your final exam? So let's make a quick list, not nearly as long as Dr. Lewis's list over here, which I think is kind of, oh, I know what the other thing I want to ask was, do any of you get to have a cheat sheet? I see some yeses. So I think Alameda's class gets to have a cheat sheet. Nice. But Lewis, no. Varn, no. Yeah, I'm not surprised either. Yeah. So for those of you in Lewis's class, really, I think it's a good thing. As I said last Tuesday, I think it's a good thing for all of you to do. Whether or not you actually get to use one, it's a good practice in kind of thinking about what you think is important and kind of identifying, oh yeah, I need to know the product rule. I need to know the chain rule. I need to know these things to be prepared for the exam. Whether or not you get to have a cheat sheet for them. If you write it down enough, you'll start to just know it. And again, that's the other thing I want to say is, from now until your test on Wednesday. Now, I know you have other exams, right? It's not just a math final, but you should be spending as much time as you can dedicate doing math problems, right? Not reading math problems, not looking at someone else's work, although you should look at the solutions I write up. But really, the way you're actually going to get better at the thing you need to get better at is doing more problems. End of story. So yes, you should look at the solutions I posted after you have done the problems yourself, right? Right. Okay. So anyway, that's all I have to say about that. I mean, not really. I could say it again and again and again, but I'll try not to. So what's on our final? Our final, like I'm taking it. What's on your final? So chapter 1. What can we expect to see from chapter 1? Limits. I think limits are actually chapter 2, though. So looking at the syllabus we have right here, limits are chapter 2. So we'll get there in a second. But chapter 1, I think log sequences. Sure, we probably some sequences. Limits of sequences, I suppose, do come up there. Although I think that actually comes up in chapter 2, but we can say, sure. No, it actually is chapter 1, yeah. Limits of sequences. So typically limits as n goes to infinity, like the limit as n goes to infinity of 3n plus 1 over 5n squared plus 2, or something like that. The other thing that I'm thinking about in chapter 1 is the log, semi-log stuff. And I think the thing you really probably need to be most aware of, if it comes up again, right? Not everything is going to show up on your final exam. It's just not, I mean, okay, maybe if you're in Dell's class, he might put everything on there. But most teachers try not to put everything on the final because it's just not possible. So for the log, the things I think you need to remember here mostly are that if you have a graph that is linear on a log scale, so linear on log translates to what kind of original relationship? Is it exponential or is it power? It's power. It's power. And then the other one, linear on a semi-log, translates to exponential. Obviously, there's a lot more to that as far as like the equation getting from one to the other, but that's kind of broadly what you need to be thinking about. To me, that's the highlights of chapter 1, right? Sure, there's a lot of other pre-calculus stuff in there, but all those topics kind of get embedded into the things you're doing with calculus. They're not going to be like asking you just straight up pre-calculus questions mostly. Chapter 2. Also, you should feel free to interject if you think there's something that I am not mentioning. Chapter 2 is mostly limits. Oh, mostly limits and something else. and continuity. I think, right? Let's see, yeah, continuity. But limits, right? So limits like the 0/0 kind, or where you have the limit as x goes to infinity, or the limit as x approaches a. You also have the kinds that are like not 0/0. But really, all of this, although it is chapter 2 material, I think most of this is going to get sucked up into when you get asked questions about limits. It's probably going to be on the L'Hopital's rule side of things. So when you see a limit on your final exam, not that you have to use L'Hopital's rule, but a lot of them probably will be L'Hopital's rule, assuming everyone has covered L'Hopital's rule. Everyone's covered L'Hopital's rule? There's no like this? Okay, good. L'Hopital's rule, you will use it a little bit in future classes, so it's definitely important that it gets covered. So most of the limits you're going to see, probably you should be thinking, can I use L'Hopital's rule? And we can only use L'Hopital's rule if we have what kind of fraction? Right, specifically, right. So if it's a fraction that's indeterminate, it is one of these two forms, either 0/0 or some sort of infinity over some sort of infinity. It has to look like that to use L'Hopital's rule. But that's kind of, again, I know limits are a big kind of topic, but that's kind of, right, chapter 2 is limits, and then also continuity. So we could see asking a question like, where is the following function continuous? Like, where is f of x equal to the square root of x plus 4 over x squared minus 9 continuous? Meaning really figure out where it's not continuous and then include everything else. We can come back to that in a minute, but right now we're just listing things. We're not doing problems yet. And then 2 more chapters, right? Which chapter 3 feels like it's kind of a big chapter. So chapter 3 is kind of everything. Really not that. How helpful, right? So chapter 3 is like all the derivative things you're supposed to know, right? Derivatives. So I would say you might get asked a question about the limit definition of the derivative. You might not. Some people are like, well, we did it in test 1. We're beyond that now. You could ask your teacher, is there going to be a limit definition of the derivative question on our test? The worst they say is, I can't tell you. It never hurts to ask. I mean, some people get annoyed, fine. It might hurt a little bit to ask, but like, if you don't ask, you won't know, right? The squeaky wheel gets the grease and all that kind of jazz. All right, limit definition of the derivative, and then like all the derivative rules. I should say derivative rules and just derivatives. So the rules are like power rule, product rule, quotient rule, chain rule. And then there's like all the functions you have to be able to differentiate. So like everything. So we can take, in fact, let's just make a whole list right now. We might as well, of the basic functions you know how to differentiate. So certainly we know the power rule. We know the derivative of x to a power is that power times x to the power minus 1. We know that the derivative of e to the x is e to the x. We know that the derivative of a different base to the x is that base to the x times the natural log of that base. We know that the derivative of the natural log of x is 1 over x. If you have a different base, like log base b of x, the derivative is 1 over x times the natural log of the base in the denominator. And then after those, it's the trig functions. So you've got sine of x, whose derivative is cosine. You've got cosine of x, whose derivative is negative sine of x. You have tangent of x, whose derivative is secant squared of x. You have cotangent of x, whose derivative is negative cosecant squared of x. You have secant of x, whose derivative is secant x tangent x. And the last trig function, cosecant of x, whose derivative is negative cosecant of x cotangent of x. Are we missing anything? I can think of one more thing. Arctangent. Kind of a trig function, but not really. It's an inverse trig function. Its derivative is 1 over 1 plus x squared. So you should definitely know all those derivatives. And you will definitely need them next quarter. So you shouldn't just know them for your final. You should know them because you're going to need to know them next quarter when we start talking about antiderivatives. I'll point out right now, because might as well, the antiderivatives you just read from right to left. So I'll say the derivative of sine is cosine. The antiderivative of cosine is sine. The antiderivative of secant squared of x is tangent of x. We'll stop there because we don't need to talk about antiderivatives right now. But definitely that's next quarter, right? So I know everybody really wants to do some math over winter break. Over winter break, you should make some derivative flashcards. And they work. I know flashcards are very old and like you have to like carry them around, but it works, right? Things work because they work. So I would recommend making some flashcards or doing something so that you remember what your derivatives are, so that you'll be a pro when it comes to antiderivatives. All right, what else is in chapter 3 though, besides all these derivative things? We also have implicit differentiation. We have related rates. Everyone's favorite. We have exponential growth and decay. So like your y equals ce to the kt stuff. There's also Newton's law of cooling in there, where it's, the way I remember it is like your temperature minus your surrounding temperature is equal to ce to the kt. That's how I remember the Newton's law of cooling thing. And then we have lovely, linearization. Chapter 3 is a lot. There's a lot of stuff in chapter 3. Okay. Not unmanageable, right? Just things to look at, things to practice. Okay, we'll briefly talk about chapter 4 and then we can do some problems. So again, right, we're just listing things so that we know what to be, right? You should be thinking about, okay, I should practice, like, if you feel weak on one of those things, find some practice problems, right? There's lots of sources on Canvas and then on paper right there. Find problems. So let's see here. Finally, chapter 4. And your chapter 4 experience might differ from your classmates because not everyone got as far in chapter 4. So we definitely have what I would broadly call all the graphing stuff. I know that's kind of a big topic, but to me, all the graphing stuff includes like your first derivative stuff. So where a function is increasing/decreasing, or as the syllabus says, monotonicity, increasing, decreasing, concavity, so concave up, concave down. Along with the increasing, decreasing, that's how we find relative extrema, so relative max and min, using the first derivative test. Concavity, that's how we find, inflection points. What else? What other graphing stuff is there that I'm not thinking about here? That's actually most of it, really. Yeah. What the heck is that? So I'm just looking at the syllabus here. It says graphing. Examples including sigmoidal curves. What the is a sigmoidal curve? I don't know what a sigmoidal curve is. It's probably not that important. But I'm curious why it's on there. I'm gonna have to look that up later. If it's important, I'll let you know. I don't think it's important though. The other thing I will point out is, aside from all the graphing stuff, which I kind of think of this as all the graphing stuff, there's also absolute extrema. So absolute max, absolute min, that's usually on a closed interval. So like, for example, find the absolute maximum and minimum of f of x equal to x to the 4th minus 4x cubed on the interval from -1 to 5. That's an example of a problem where you could do the thing. And we will do that, just not right now. What else is on this list? Okay, here's where we might start. Well, I hopefully, okay, raise your hand if your class didn't cover L'Hopital's rule. Good, thank goodness. Okay, so everyone's got L'Hopital's rule. And that just says the limit as x approaches a of f of x over g of x. If it's equal to a 0 over 0 or an infinity over infinity, doesn't matter if it's a plus or minus, then you can say the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime of x over g prime of x. Optimization. Did anybody not cover optimization? Good, okay. Okay, well, we'll talk about it for, we'll see. And then I don't think, I don't know, I know Didel's class after this, but did anybody get the stability of fixed points? Talking about finding the equilibria of a recursion, maybe doing some cobwebbing, which is a graphical method. Did anybody do that in their class? Good. Good, not good that you didn't do it. Good that nobody did it, right? Better, good that we're all on the same page so that I don't have to cover it for some people and then not be like, everyone's like, well, James, we didn't. Yeah, okay. So that part is not super duper important, but no, yeah, it's not that important. I mean, it is important, but like, yeah, you get what you get. All right. So somebody definitely did ask if we could do some optimization examples. So we'll start there because that's where we're going to start. But are there any, I should stop asking. If you have questions, comments, or concerns, you should just raise your hand and say them or ask them. So I will keep moving. You should ask questions if you got them. So optimization. Yes. Oh, yeah, like, okay. Yeah, what chapter is that? Sure, we can do an example like that. So yeah, they're the typically we call it kinematics or motion problems where you have like an object often thrown into the air and falls with gravity. Yeah, we can definitely do a problem like that and pick kind of the usual things. But so here's a couple optimization problems that somebody sent me that we can look at. I don't know if I love that one so much. We can definitely look at this other one here. So to me, these feel kind of atypical, but they are in the textbook. So let's take a look at them. So here's this first one on, this is question number 24 from section 4. I don't know if it's 4.3 or it should be section 4.4. Problem number 24. So here's what we've got. Lots of words. These problems always have lots of words. I guess I can start writing. Suppose that instead of, now this problem refers back to an example in the book, which we'll look at in a second. Instead of the specific oxygen function in example 4, we have an arbitrary function O, which is a terrible name for a function, with O of 0 equal to 0. Why that you can see maybe why O is a terrible name for a function. We're also given that O at any time is bigger than or equal to 0. The derivative of O at any time is also bigger than 0. And the second derivative of O at any time is less than 0. So this says interpret the conditions on the function O. Okay, that's not a terrible question if we know what it means. Let's go back and look at example 4 real quick, just so we make sure we know what we're talking about. All right, did I not bring my book? I thought I had, no, yeah, it's right here. Like I thought I had my book. So 4.4 example 4. So here is the problem that they start off with that they're referring to. Aquatic birds forage underwater and periodically return to the surface to replenish their oxygen stores. Oxygen stores increase with the amount of time spent on the surface, but in a diminishing way, according to this model. So basically, the amount of oxygen you get as a function of time is 20 times time over 5 plus time. So the longer you spend above the water, the more oxygen you're going to get. But eventually, time starts to like peter out, right? Like if you let t go to infinity, this is going to get closer and closer and closer to 20. But if you let t equal like 5, you might be pretty close anyway. So, right, diminishing returns. Yeah, that's all I have to say about that, really. So, if we look at this here, what do all these things mean? Is what they're asking. Well, O of 0 equal to 0 means at the very moment when we surface from the water, how much oxygen do we have? Right. We have 0 units of oxygen. I don't know what the units are. Let's just say units of oxygen at time equal to 0. I'll point out that's time, that's amount of oxygen. Okay, what about this next condition? What does it mean that O of t is greater than or equal to 0? Well, O of t is the amount of oxygen, so it means our amount of oxygen can't be negative, which seems reasonable, right? You can't have I mean, I don't think you could. Like, could you expel, could you have a negative? No, I don't think that's possible, right? You can't have a negative amount of oxygen in your lungs. Like, unless you like take your lungs out of your body, maybe, then maybe, I don't know. That's no. Okay. So non-negative amount of oxygen in the body or the lungs or wherever it is. Let's just say the body. I'm not a biologist. Okay, here's a more interesting question. What does it mean that O prime of t is greater than 0? Well, very basically, it means the derivative is positive. But as far as the function, what does that actually mean about the amount of oxygen? Is it increasing or is it decreasing? The derivative is positive. Right. The amount of oxygen is increasing. Finally, O double prime of t is negative. Oh, okay. Here's what I would do. I would draw a picture where the function is both positive, increasing, and concave down. So I'm thinking of something that looks kind of like the square root function. It's not perfect, but it's good enough for the moment. This function certainly is increasing, certainly is positive, right? It's always above the x-axis, and it is concave down. You can think of that as, my favorite way of thinking of this now is that any tangent line I draw is above the graph. And that's a way of thinking about something being concave down, or it's opening downwards. So what that means is that it's really increasing fast at the beginning, but then as we go along, it's still increasing, but less fast. So the rate at which we're increasing decreases, which goes kind of back to what they said about how it has diminishing returns as you go on and on and on. So the rate of increase decreases. All right. I'm not exactly trying to answer this next question. These questions feel very kind of challenging. Let's do this next part though. So we'll look at this. I don't know. I don't love this one either. So let's mention this for a moment. So they want us to show that the optimal surface time satisfies the equation O prime of t minus r times, yeah, this is not something we should spend time doing. Yeah, that's not going to be helpful to us. It's not a bad question, but I think this is a no. This is a no. This is a no. Sorry, apologize. I apologize for showing you that question. Not the first part. I think the first part was definitely worth thinking about. Second part, though, no one's going to ask you that in a final, or they shouldn't. Okay. The other one we're looking at here. Oh yeah, this other one's much better. Okay. Well, let's look at this other question, which is question 19 from the same section. And then we'll look at a few other ones. So here's the setup here. If C of X is the cost of producing X units of a commodity, then the average cost per unit is, well, the cost divided by the number of units, C of X divided by X. The marginal cost, so average cost per unit, the marginal cost, which is something that's interesting to think about, is the rate of change of the cost with respect to the number of items produced. That is, it's the derivative. C prime of X. So I do like this first question. Show that if the average cost is a minimum, then the marginal cost is equal to the average cost. Kind of a confusing question, right? There's a lot of words that are like, what are they really saying? A lot of these questions are about interpreting what's going on. So they told us what all the things were. We just have to figure out what they mean. So they want us to show that if the average cost is a minimum, okay, how do we minimize something? If I have a function f of x, and I want to find where it has a minimum or a maximum, what do? Take the derivative and, right, find the critical point. Set it equal to 0 / undefined and see what we get. Okay, great. So we're going to take, well, but the average cost is this thing right here. So we're going to take our average cost, which I'm going to call A of X for a second, equal to C of X over X. And we're going to take the derivative and set it equal to 0. So we're going to differentiate and set equal to 0. Okay, well, for C of X over X, I'm going to have to use the quotient rule. So that's going to be the bottom times the derivative of the top. I don't know what C of X is, so I'm just going to write C prime of X minus the top times the derivative of the bottom, which is 1, all divided by the bottom squared. And we're going to set this either equal to 0 or undefined. I will point out that it doesn't really make sense for this to ever be undefined, because for this to be undefined, X would have to be 0. And we're not producing 0 units of our product, right? Not if we're trying to make money. So this function isn't really undefined, or this derivative isn't ever undefined in a sensible way. But if we set this equal to 0, well, we're setting the top equal to 0. So that's going to be X times C prime of X minus C of X equal to 0. Okay, great. So we've kind of found where we have a critical point, or at least we found the idea of what we would do to get the critical point. But now let's go back and read the question again. We want to show that if the average cost is a minimum, which we would get by setting the derivative equal to 0 and hopefully being the right thing, then the marginal cost is equal to the average cost. Well, the marginal cost, that's just your derivative. And the average cost, that's your cost divided by X. So could I take this equation and somehow get that the derivative is equal to the average? I think I could. Right, let's try and isolate the derivative. So I'm going to say that x times c prime of x equals c of x. And then divide both sides by x to, oh yeah, look, I exactly get the thing they're telling me I'm going to get. That by taking the derivative of this thing and setting it equal to 0, I'm actually getting that the marginal cost has to equal the average cost. Kind of neat. Okay, let's look at the question with some real numbers because this seems like a little hand wavy. So let's say we're given, still in the same situation here, but now we're actually given a cost function. So given cost equal to 16,000 plus 200x plus 4x to the 3 halves in dollars. We want to find the production level that will minimize average cost. So let's be careful here. They're not asking us to minimize the function they just gave us. They didn't give us the average cost function. They gave us the cost function. So the average cost is equal to c of x divided by x, which is, we could write the whole thing divided by x, but it's going to be more useful to write just each thing divided by x. That's going to be like 16,000 divided by x plus 200x divided by x plus 4x to the 3 halves divided by x. We should simplify that before we take the derivative. That's going to equal 16,000. Am I making this harder on myself than I need to? No, I don't think so. Maybe, I don't know. We'll find out. 16,000 x to the negative 1 plus 200 plus 4x to the 1 half. So now we're going to differentiate. So the derivative of c of x over x is going to be negative 16,000 x to the negative 2 plus 0 plus 1 half times 4 times x to the negative 1 half. Kind of terrible. Set that equal to 0. And here's what we should do. We should definitely do some rewriting. So I'm going to rewrite this as negative 16,000 over x squared. This I'm going to rewrite as 1 half times 4 is 2. X to the negative 1 half is dividing by x to the positive 1 half. Equal to 0. I would bring everything, well, I wouldn't. Actually, I would bring this to the right. So I'm going to say that I have 2 over x to the 1 half equals 16,000 over x squared, and then cross multiply. So that 2x squared equals 16,000 x to the 1 half. Divide both sides by 2. So x squared equals 8,000 times x to the 1 half. Divide both sides by x to the 1 half. So the x to the 3 halves power equals 8,000. So then solving for x is going to equal 8,000 to the 2/3 power, which is a nice number. What's the cube root of 8,000? Yeah, 20. So this is going to equal 20 squared, which is 400. Does it minimize it? Or is it a maximum? Did we find the value? Did we find the number of things we produced that would maximize the cost? That'd be really not great. So the point here is that you kind of have to check, or I don't know. It depends on what your teacher asks you. Often you won't be asked to actually check if it's a maximum or minimum. So how do we check if it's a minimum? You use the first derivative test, right? It's your only critical value. So you can say, well, my domain here is kind of 0 to infinity. My critical value is 400. And if I look at what's going on with the first derivative of this thing, well, if I look at this simplified form here, If I plug in a number like 1, I always go as small as possible. If I'm going away from the critical value, I'm going to go either really small or really big. If I plug in 1, I'm getting negative 16,000 plus 2, which is for sure negative. If I plug in something really big, like a billion, I'm getting negative 16,000 over a billion, which is pretty close to 0, plus 2 over the square root of a billion, which is also close to 0, but not quite as close. I think, yeah, because right, the squaring is going to make that much, much smaller. Also, if it's minus here and we expect it to be a minimum, so honestly, if I was actually doing this on the test, what I would really do is be like, yeah, I checked. It definitely worked out. Did you not see me check the numbers? I checked them, right? For real though, like you can do that. If you know it's supposed to be a minimum and you're supposed to check, you're like, yeah, I checked. There's my sign chart that shows I checked. So we definitely do have a minimum at x equal to 400. And the minimum value, the minimum average cost would be, if they asked you that, you would plug that value 400 back into the average cost. So it'd be 16,000 divided by 400 plus 200 times 400 divided by 400, which is 200, plus 4 times the square root of 400. And that does simplify pretty nicely. That would be 40 plus 200 plus 4 times 20, which is 320. Yeah. So in my mind, these are not the optimization problems that I'm used to kind of thinking about, but they are the kind of optimization problems that are more likely to show up in this class. I'm more used to the ones where you have like like you're trying to, I don't know, maximize the area of the thing that's inside of another thing. So, but I don't want to waste your time with that. Although, I don't know, let's actually, let me see one thing here real quick. I'm curious. I'm curious about what's on Alameda's practice file here. Does he have any interesting optimization problems? I see a lot of limits on this practice test. Like just so everyone can see here. Here's Alameda's practice final. A limit, 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 a limit. Maybe we should talk about limits. I see a related rates problem. I see an optimization problem that's pretty standard. Let's do this one. And yeah. Interesting choices there. All right, so let's look at one more optimization problem that's more of the style that you might expect. Then we can talk about some limits. So yeah, sure. So suppose I'm gonna switch this problem up a little bit. So suppose that we want to construct a box with an open top that can hold a volume of 32 cubic feet. Also, the box has a square base, which I should have said earlier. So I'm imagining like a milk carton kind of, except it doesn't have a top. Milk carton's probably not a good example. What dimensions minimize the amount of material needed, aka surface area, to construct the box? This is a pretty typical type of optimization question. I feel like that looks a little blurry. Let's see if that helps a little bit. Sure, maybe it's just my writing is a little blurry. There we go. So suppose that we want to construct a box with an open top and a square base. that can hold a volume of 32 cubic feet. What dimensions minimize the amount of material needed to construct the box? Let's draw ourselves a little box over here. So here's our box. It's got a open top and a square base. We don't know the length of any side, so we should give them variable labels. Typically, I'm going to pick X for this side, also X for this side because the base is square, and then not X for this side, usually Y or H or something like that. Typically with an optimization problem, well, I should say, typically in my mind, unlike the previous examples, we have to come up with the equations here, right? They're not going to give us the equations for these. So we have to come up with the thing we want to minimize, which is the surface area. Surface area isn't too bad here. The surface area is equal to the area of the bottom, which is X squared, plus the area of the sides, which are each X times Y. And how many sides are there? Well, if it was a closed top, there'd be 6 total. But how many are there around? Yeah, just 4. So there's 4 sides that each have an area of X times Y. That's the thing we're trying to optimize, in this case, minimize. So it shouldn't be equal to a number yet because we don't know what it is, right? We're trying to figure out what the minimum value is. On the other hand, we also have a constraint. We know that we want the volume, whose equation is X times Y, or X squared times Y. The volume should be 32 cubic feet. So very typically for optimization problems, there's something you're trying to optimize and there's some constraint that is making you work for it, essentially, right? You don't just get to have whatever you want. You have to adhere to this requirement. So then usually our process is to, after finding the thing you want to optimize and your constraint, to isolate one of the variables in your constraint, usually the easier one. So if I had to isolate X or Y, I would pick Y because I don't want to take a square root of both sides. So I'm going to isolate Y and get Y equal to 32 divided by X squared. It's right there. And then after that, plug that into your thing you're trying to minimize that usually has too many variables in it, right? The reason we're doing this is because surface area depends on both X and Y, and I don't know how to maximize or minimize a function of 2 variables yet. You will in 17C. But here, we're going to plug that in. We're going to get surface area equal to X squared plus 4 times X times 32 over X squared. Okay, we're trying to minimize surface area, so what are we going to do? What are we always going to do? We're trying to minimize, maximize something. Find the critical values. Take the derivative, set it equal to 0, see what we get. And again, just like every time we take a derivative, it's really in our interest to simplify the thing before we differentiate it. So I should definitely rewrite this as X squared plus 4 times 32 is 128, and X over X squared reduces to just 1 X in the denominator. Or even better, X squared plus 128 times X to the negative first. So that now when I take the derivative, when I find the critical values, my derivative is going to equal 2x minus 128 x to the negative first, and that's going to be equal to 0. Technically, this is also undefined if x were equal to 0, but would x equal to 0 make sense as an answer? Definitely not. If x were 0, the volume couldn't be 32. Right? Technically, actually 0 is not in the domain of this function, right? Because 0 would give you a volume that wasn't 32. So take this equation, solve for x. So I'm going to bring the 128 x to the negative first over to the other side and write it as positive 128 over x. I'm going to multiply both sides by x. I'm going to divide both sides by 2. I'm going to get x equal to 8. Not plus or minus 8, just 8. Oh, question, yeah. Thank you. Yes, it would. Oh my goodness. I've made that mistake before. Sorry about that. Good call. Thank you. So we really should have 2x minus 128 times x to the negative second equal to 0. So 2x equals 128 divided by x squared. So 2x cubed equals 128. So x cubed equals 64. So x equals the cube root of 64, which is 4. not the square root of 64, which is 8. Okay, good call. Thank you. Questions about that process? Okay, did we do the thing we wanted to do? Does this actually minimize the surface area? Bless you. Well, again, let's check. So here's my domain where we're starting at 0 because it doesn't make sense to be less than 0 and going to infinity. And we say, great, well, at 4, pick a number less than 4, like 1, and plug it into this. 2 minus 128 is definitely negative. Pick a number like 10 and plug it in. 20 minus 128 over 10 squared is certainly positive. So yeah, it's decreasing, increasing. Yes, we have a minimum. Or you could use the second derivative test. You can take the second derivative here and say that SA double prime is equal to 2 plus 128 times x to the negative, sorry, 256, oh my goodness, x to the negative third. And if you plug in your critical value of 4, you can see that, sorry, and I'm squeezing things in here like a terrible person here. The s double prime of 4 is certainly going to be a positive number, which means it's concave up, which means you have a minimum. That's another way of testing to see if your critical value gives you what you want. Concave up means you have a minimum. Yeah. Because so yes, that's a fair question. Let me show the work a little bit more legibly, maybe. So I'll remind, so the first derivative was 2x minus 128 x to the negative second. The second derivative is equal to 2 plus 256 x to the negative third. If I plug in the critical value from the first derivative, which was 4, I get 2 plus 256 times 4 to the negative third. I don't really care what this number is. I just care if it's positive or negative. And I can totally see that this number, well, that's 2 plus 256 divided by 4 cubed. Whatever that is, 2 plus that is certainly going to be positive. But if your second derivative is positive, right, s double prime of 4 being positive, that's equivalent to your original function being concave up. So positive second derivative means your function opens upwards. But that means if your function is opening upwards and you have a critical point, it either has to be a max or a min. And if it's opening upwards, it has to be a minimum. That's the gist of the second derivative test for critical values. But either way you want to show it is fine. You can show it this way using the first derivative test. You can show it this way using the second derivative test if finding the second derivative isn't too terrible. Sometimes it really is. Here it was not. So then we still haven't answered the question though, because the question said, what dimensions, plural, minimize the surface area of the box? We found the x dimension, which was 4 feet. We still have to find the y dimension. Now, the good news is, if you're trying to find the other dimension, there's almost always an equation on your page already that has that dimension isolated. Specifically, when we went back here and we isolated y, we have y equal to 32 over x squared. So if we know that x is equal to 4 feet, then y is going to equal 32 divided by 4 squared, which is 32 over 16, which is 2 feet. So those are the dimensions. 4 on the bottom, 2 on the vertical. So not like I drew it at all, right? The box is definitely much shorter than it is wide, which is fine. All right. Optimization. Okay, so let's do one kinematics problem as requested, and then we'll look at some of these limits. So, motion / kinematics. Sure, let me think for just 1 second here. Yeah. A ball is thrown upward from the top of a, sorry, I'm trying to make sure the numbers work here. Yep, that'll work. Of a 96-foot tall building with an initial velocity of 80 feet per second, which is really fast. It's not that. To throw a ball straight up is pretty fast. Like, it's hard to throw a ball straight up. Have you ever tried? It's not that. That's not easy. Maybe trying to like this is much harder than doing like that. Anyway, we're gonna ask the typical questions. Here are the typical questions. What is the maximum height of the ball? And how fast is the ball going when it strikes the ground? People often break these questions up into like 4 questions, but I could also see asking them just like this. So question A, max height. I guess we need to give us, I guess we probably need to be given the equations as well. So I don't know if you're going to be given these equations or expected to know them, but typically here's how the equations for height and velocity and acceleration work for objects falling. The height of the object at time t is given by -16 times t squared plus the initial velocity times t plus the initial height. That is your typical height equation for an object falling due to gravity. And then your velocity is just the derivative of position. So it's -32t plus whatever your initial velocity is plus 0. And then if you care, the acceleration is just -32, which is the acceleration due to gravity, -32 feet per second per second. And sometimes people make you use antiderivatives to go from this to that. So I'll point out that v of t is the derivative of h of t, and the a of t is the derivative of v of t, which is the second derivative of h of t. Well, let's assume we've been given. So then, if I want to find the maximum height, and I guess I should write, so our height function for this specific example would be -16t squared plus 80t plus 96. So if you want to find the maximum height, we first have to be able to maximize the function. How do you maximize the function? Take its derivative, set equal to 0. We know it's going to have a maximum because the shape of this graph is a downward opening parabola, right? It's definitely a parabola. It's a quadratic equation. We know it's a parabola looking thing, and it's opening downwards because of the negative sign right there. So we know it's going to look something like that. It's certainly going to have a maximum. You could probably even kind of cheat and just be like, oh, it's the vertex, and find the vertex if you want to do it that way. But you should do it using calculus. So we're going to take the derivative, which is v of t, or h prime of t. And that's going to be our -32t plus 80, and we're going to set that equal to 0. And then solve for t. So 80 is equal to +32 times t. So t is going to equal 80 divided by 32, which reduces to 40 over 16, which reduces to 20 over 8, which reduces to 10 over 4, which reduces to 5 over 2. So we know that it's going to take 2.5 seconds to reach the maximum height. That wasn't the question, though. The question wasn't, when do we get a maximum height? The question was, what is the maximum height? So then to find the maximum height, we have to plug that 2.5 seconds back into the height function. So the maximum height is going to be the height function evaluated at 5/2, which is going to equal -16 times 5/2 squared plus 80 times 5/2 plus 96. This probably actually isn't terrible because I think all the fractions kind of cancel out. This is negative 16 times 25 over 4. And you can cancel a 4 here and a 4 here. And then plus the 80 and the 2 cancel to give you a 40 times 5, which is 200. And then plus 96. So we get negative 4 times 25, so negative 100 plus 296 is 196 feet high. Okay. So to find the maximum height, you have to find when the thing reaches its maximum height and then plug that time into the height function to find what the maximum height is. We're going to answer the other question in the same way. The other question is, how fast, so what's the velocity, is the ball going when it strikes the ground? So first we have to figure out when it strikes the ground. So how do you know when the ball strikes the ground? Well, what's 0? Not the velocity. So certainly after the ball strikes the ground, yes, it stops moving and its velocity is 0. But when it hits the ground, it's going really fast. Its velocity is certainly not 0. What is 0 though? The height, right? I'm down on the ground, which we're typically calling a height of 0. So we're going to set the height equal to 0 and then solve for what time it is when the height is 0. So we're going to set for part B here to find the velocity when it hits the ground. We're going to set first the height, which was negative 16t squared plus 80t plus 96 equal to 0 to find the when. Now, if this problem has been written in a kind way, you'll be able to factor out a negative 16, which we can here. So we can factor out a negative 16, and we're left with t squared. 80 divided by negative 16 is negative 5, and 96 divided by negative 16 is negative 6. You definitely do want to either divide both sides by 16 or negative 16 or factor out the negative 16 if you can. Now, if it's not kind, it might, or if it's in metric, then it's probably not as nice, and you might have to use the quadratic equation. Here, this works out great. So then we can factor this further as t minus 6 times t plus 1 equal to 0. So what time is it when the ball hits the ground? How many seconds have elapsed? Which of those answers makes sense? 6, right? You can't go back in time. We're not sure. Sorry for my. If I could turn back time. It's a good song. You should back and turn. Okay. Anyway, sorry. Anyway, it's the end of the quarter. What can you say? So the ball hits the ground when time equals 6, and then to find the velocity, we're going to take our velocity equation, which was negative 32t plus 80, and plug in 6. So velocity at time 6 is equal to negative 32 times 6 plus 80. Negative 32 times 6 is negative 192. Plus 80 is negative 112 feet per second. So here's what we have to make sure we're answering. Are they asking us what the velocity is or what the speed is? Well, I wasn't very specific, unfortunately. I feel like the way I phrased the question probably is speed, right? It says, how fast is the ball going when it strikes the ground? I think you could say the speed is just 112 feet per second. The velocity is negative 112 feet per second. The difference between speed and velocity is speed is just always positive, right? You're just saying, how fast was I going? Direction doesn't matter. Velocity is speed along with a direction. And in this situation, we're typically imagining the ball traveling up as having a positive velocity and the ball traveling down, which it is at this moment, having a negative velocity. So if they ask for the velocity, say, oh, it's going at negative 112 feet per second because it's going down. All right, let's go ahead and spend the remaining 14 minutes looking at these terrible limits, which there's a lot of here, which makes you think you should probably, if you're in Alameda's class, brush up on some limits. Let's take a look. So Also, I would encourage all of you in his class to make sure you read these instructions, right? It's always good to read the instructions for the problems and for the test. So, I'm all out of order here. Let's see what we've got here. Compute the following limit using any method you are familiar with. You must show your work. Oh, I'm sorry, you can't see that. Apologies. So, for this limit here, what should I do first? Before I simplify, plug in the thing x is approaching. See what you get. You might just get a number, right? So you should always check, because sometimes people like to be sneaky. So if we plug in 0, we get 0 times sine of 0 over 1 minus 1, which is 0 over 0. Okay, it's a 0 over 0. Not surprising. So then I would probably use L'Hopital's rule if it's a 0 over 0. Not that there aren't other ways to do this, but it's probably the best way. So using L'Hopital's rule, we're going to take the derivative of the top using the product rule. So it's going to be 1 times sine of 2x plus x times the derivative of sine of 2x, which is cosine of 2x times 2, divided by the derivative of the bottom, which is 0 minus a minus is plus sine of 3x times 3. And then we should see what happens if we plug in 0 again. Do make sure when you use L'Hopital's rule that you're writing the limit again. So if we plug in 0, sine of 0 is 0. 0 times stuff is also 0. And sine is, I think we're going to get 0 over 0 again. So what does that mean? Use L'Hopital's rule again. If I'm using L'Hopital's rule again, I would probably do a tiny bit of simplification first. I'd probably rewrite this as the limit as x approaches 0. On top, I have sine of 2x plus, I would write this as 2x times cosine of 2x. On the bottom, I have 3 times sine of 3x. Okay, let's use L'Hopital's rule again. So now we're going to get the limit as x approaches 0. Derivative of the top, okay. The derivative of sine of 2x is cosine of 2x times 2. And over here, we're going to have to use the product rule again. The derivative of 2x is 2 times leave cosine of 2x alone. Plus, now we leave 2x alone. And the derivative of cosine of 2x is negative sine of 2x times 2. All divided by 3 times the derivative of sine of 3x is cosine of 3x times 3. Now, if I think about plugging in 0 here, I know I'm going to be done. Because I know that when I plug in 0, I won't get 0 in the denominator. Right? Cosine of 0 is 1. So I'm for sure done using L'Hopital's rule here. It's not going to be a 0 over 0 or infinity over infinity type. So if we plug in 0, I feel safe writing it all out. I'm going to get cosine of 0, which is 1 times 2, plus 2 times cosine of 0, which is also 1, plus 2 times 0, I don't even need to write the rest, that's just 0, over 3 times cosine of 0, which is 1 times 3. So at the end of the day, I have 2 plus 2 over 9, so 4 over 9. Kind of gross. All right, let's look at the next one. Same instructions. Use any method you want. You must show your work. So what should I do first? Plug it in. Let's see what happens. Negative 2 squared is 4. Minus 2 is 0. On the bottom, 2 times negative 2 squared is 4. Minus 8. Yep, it's still a 0 over 0. It's good to check, though. At least mentally, right? You don't have to write it down necessarily, but definitely at least think about, if I plug in negative 2, do I actually get 0 over 0? You could use L'Hopital's rule here. That's a totally fine way of doing this. We use L'Hopital's rule. Use the limit as x approaches negative 2. The derivative of the top is 2x plus 1. The derivative of the bottom is 4x. What do I do now? Plug it in. So my answer is going to be 2 times negative 2 plus 1 over 4 times negative 2, which is negative 4 plus 1 over negative 8, which we should simplify as 3/8. Alternatively, if you don't like L'Hopital's rule, although I don't know why you wouldn't like L'Hopital's rule here, it's pretty great, but you could also have factored this if you wanted to. You can rewrite the limit as x approaches -2 of x squared plus x minus 2 over 2x squared minus 8. The top factors as x plus 2 times x minus 1. The bottom factors as 2 times x squared minus 4, which is 2 times x plus 2 times x minus 2. Those cancel. You plug in -2, and you get -2 minus 1 over 2 times -2 minus 2. That's -3 over -8, which is the same thing. Totally find the factor there if you like. All right, let's look at some more limits. There's so many of them. Ugh. Compute the following limit using any method. You must show your work. Okay, we get the idea. So here, if you plug in infinity, the square root of infinity is infinity. And that's also going to infinity. Infinity minus infinity is an indeterminate form. Most of these limits are going to be indeterminate forms. Otherwise, they're not very exciting. Well, shoot, what do we do now? We can't use L'Hopital's rule, right? It's not 0 over 0, infinity over infinity. Right. Usually when you see a square root, that almost always means we multiply by the conjugate divided by the conjugate. Right? Because you have to multiply by 1. So we're going to write this as the limit as x goes to infinity of the square root of 4x squared plus x minus 2x over 1 times the conjugate, which is the square root of 4x squared plus x plus 2x over the same square root of 4x squared plus x plus 2x. Multiplying out the top, because you always actually multiply out the conjugates, you're going to get the square root of 4x squared plus x times the square root of 4x squared plus x, which is just 4x squared plus x. The middle terms cancel out. That's the whole reason we multiply by the conjugate every time. And then the end term is minus 2x times 2x, which is minus 4x squared. All divided by the square root of 4x squared plus x plus 2x. And I see a really easy simplification for the numerator. The 4x squareds cancel. So we can rewrite this as the limit as x goes to infinity of x over the square root of 4x squared plus x plus 2x. And now technically, you have an infinity over infinity form where you could use L'Hopital's rule. And I'm going to strongly recommend you do not. Because although I'm not entirely sure, I'm pretty sure this is one of those limits where if you use L'Hopital's rule, you don't get anywhere. Like you use it twice and you end up essentially back where you started. Like, because what happens when you use L'Hopital's rule here is it kind of flips over the fraction. And then when you do it again, it kind of flips it back. Also, it's just going to be kind of gross, right? The derivative at the bottom is not going to turn out particularly nice. So this is one where, although L'Hopital's rule might be a tool you could use, it might not actually work. And also there's probably a more direct way of getting there. Here's the more direct way. Yeah. So what we have to do here, it'd be great if we could kind of just like factor out an x from the bottom. And we're going to do that. Because essentially, well, actually, let me point out, what's the highest power of x in the numerator? Right, it's the only power of x, it's 1. And although it's kind of not true, it also kind of is true that the highest power of x in the denominator is also 1. You have an x squared there, but it's inside of a square root. And the square root of x squared is kind of like x. So here's the way we do this for real. We leave the x alone on top. And from the square root of x squared of 4x squared plus x, we're actually going to factor out inside the square root an x squared. So we're left with a 4 plus 1 over x. Plus, still we have 2x over here. If you have questions about this right now, you should ask them. Okay, now, what's the square root of x squared? Well, technically it's the absolute value of x. But since x is positive, right, it's about as positive as it gets, the absolute value of x is just x. So we can say, great, that's going to be the limit as x goes to infinity of x over the square root of x squared just becomes x outside of the square root. And inside we still have 4 plus 1 over x plus 2x. If this limit was going to negative infinity, then the x squared would come out as a negative x because the absolute value of x would be negative x if x was negative. It's kind of weird. Here, we don't have to worry about that. So then from the bottom, we can factor out an x, and we're left with x over x times the square root of 4 plus 1 over x plus 2. And now those x's get to cancel. So now we're left with the limit as x approaches infinity of 1 over the square root of 4 plus 1 over x plus 2. This remaining 1 over x is going to get really, real small. And so we're left with 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, which is 1/4. Yeah, this problem is a little funky though. It's a pretty standard process, but that doesn't mean it's easy. So when you see a square root minus something else, and it's like going infinity minus infinity, it's typically this process. I would encourage all of you, when you have a chance, I'll write up solutions to this problem here, but let's say you had almost the same problem. Let's say you had the limit as x approaches negative infinity of the square root of 9x squared plus x plus 3x. Sorry, you can't quite see that. So this is a good one to try on your own. I'm not going to do it right now, but I will do it later. But I'll point out at some point, you're going to get the square root of like x squared times 9 plus 1 over x. And when you pull out that x squared, it's going to be the square root of x squared times the square root of 9 plus 1 over x. And then it's going to be the absolute value of x times the square root of 9 plus 1 over x. But since x is going to negative infinity, the absolute value of x is going to equal negative x. Why is that the case? Well, if x is negative, what's the absolute value of -7? Right, how do you turn -7 into 7? Oh, it's -7. That's why the absolute value of x is equal to the negative of x if x is already negative. You're turning that negative into the corresponding positive number. I know it feels wrong. You're like, James, it should be positive. And I'm like, yeah, but we're trying to make it positive. It was already negative, so we need another negative sign to make it positive. I know it feels weird, but it's so for this problem here, when you're doing this one, when you do this one in very much the same way we just did the last one, you do those same kind of steps, but when you get to this stage here, this is going to equal negative x times the square root of 9 plus 1 over x. But this is a good practice problem. I encourage you all to do it. I will post solutions to it a little bit later. I will point out also, just so everyone's clear, this is also an indeterminate form, right? This part here is going to positive infinity because it's negative infinity squared, which is positive infinity, times 9 minus a smaller infinity is still infinity, plus a negative infinity. So you have an infinity plus a negative infinity. Oh, that's infinity minus infinity, which is indeterminate form. All right. I guess I should stop talking. It's 3:30. All right. So office hours right now, if you want to come. Office hours tomorrow from 2 to 4 as usual. And then next week, every day, whatever times they said they were. 11 to 12 and 1 to 4, except for Thursday, which I won't be there 11 to 12. But Grant will also be there. So find Grant if you can't find me. Find Jen if you can't find either of us. Find Sarah if she happens to be around. Yeah, what's up?
When would the online attendance be graded?
So what's gonna happen is essentially after this week, after I teach my classes tomorrow, I'll go start looking. Basically, here's what I'm gonna do. Really. I'm gonna go look and see like everyone who has a passing grade, great, they pass. Everyone that doesn't have a passing grade, I'll look to see their final attendance and add those in to then bring their grade up to whatever it's at. So sometime early next week, probably.